So in this question, we are asked to prove that one-sided identity is a two-sided identity. Okay. So first, let's understand what do we mean by a one-sided identity and a two-sided identity. Okay. So in the definition of group, the definition, what do we say of group? First and foremost, G is a set together with a binary operation, right? And this binary operation will satisfy associativity. And as the next condition, what are we saying? We are saying that there exists an element E in G, okay, such that for any A, in G, it must satisfy A into E is equal to A and E into A is equal to A, right? So whether we operate from the left or we operate from the right, it does not matter. In both the situation, the element, E acts as an identity. Okay, so here E acts as identity from both the sides. So this definition of the group imposes a two-sided identity, right? So here E, when operating from the left or from the right, it is acting as identity. So the element E is called a two-sided identity. So the definition of the group actually imposes a two-sided identity. Okay. Now, suppose we are not given this much information. Okay. Suppose just we are given that G is a group. Okay. And some element E is having the property that for any A in G, AE is equal to A. This much we are given. Okay. So let's be careful here. Here we are not given that E is the identity. Okay. We are just said that E is an element in the group G. Okay. E is in G, and it is having a property that when this element is operated from the right for any element, it does not change it. Okay. So if we were given that EA is also equal to A, then we can conclude that E is the identity from the definition. But here we are not given the other side. Okay. So the question here is to prove that the other side also automatically follows. That is, we have to show that EA is also equal to A. Okay, so what are we saying here? In the definition of the group, we said that EA must be equal to A and AE must be equal to A. So both sides it should hold. There are two conditions and both of them must hold. Now, suppose that an element in the group G satisfies one of them, one of the conditions. Say, for example, AE is equal to A. This much is satisfied. Now, the other condition, EA is equal to A, is not given to us at the moment. We are asked to deduce that the other condition, EA is equal to A, is also satisfied. Okay, we have to show that E satisfies this. Okay, this is our situation. Okay, so let's begin with this. So at present, we don't know what EA is, right? We know that EA will definitely be an element in the group. That much we know. At present, we don't know it is A or not. Okay, we only know from the right E acts as an identity. From the left, we don't know. Okay, so let X is equal to EA. We don't know what this is. So EA is. So let's call it X. The only thing we know is X is in G. Okay. Now, since G is a group, we know that A inverse will exist, right? So A inverse exists since G is a group. Okay, so we will operate on both sides by A inverse. So we will get that X A inverse is equal to identity if we are operating from the right. If we are operating from the left, what will we get? We will get that A inverse X is actually equal to A inverse into identity. A inverse into identity into A. Okay. Now let's stick to this. Okay, so what do we have here? We have that A inverse X is actually equal to A inverse into EA. All right. Now by associativity, we'll have this is equal to A inverse into E into A by associativity. All right. Now just look here. From the given condition, we know that E acts as a identity when it is operated from the left, right? This property, right? Sorry, when it is operated from the right, E acts as an identity, right? Now A inverse is an element in the group G, and E will act as an identity when it is operated from the right. So we'll have that A inverse into E must be equal to A inverse by given condition. Okay, so what will we have here? We'll have that A inverse into X is actually nothing but A inverse into A. Okay, now A inverse into A, it has to be the identity. Okay, now to avoid confusion, I am just calling the identity element in the group as 1. Okay, so we'll have that A inverse into X is equal to 1. 1 is the identity element. We know that group G is, identity element in G. We know that G is a group, so there exists some identity element. Okay, so at present I am calling it as 1. Now we have that E acts as an identity from the right. That's all we know. So at present we don't know if E equal to 1 or not, right? So we at present instead of 1 we cannot directly write E. Okay, that's why I'm giving a different notation. Okay, now let me operate by A on both sides. So we will have X is actually equal to A into 1, which is actually equal to A. Okay, but then what was X? Let X is equal to EA. So we have that EA is actually equal to A. So what happened here? Here E is acting as identity from left also, right? And this is exactly what we wanted to prove. Okay, so note here that A was any element. A was arbitrary. Okay, A was any element in the group G. We started with any element because the property is for any A in G. Okay, so we started with that. We started with an element E that is satisfying the property of being the identity element when it is acting from the right. Okay. Now we concluded that it will also be and it will also act as identity when it is operated on the left. All right. So here one-sided identity will automatically imply that it is a two-sided identity, and here E will be equal to 1. Okay, so in the definition of the group G, we are specifically demanding that it should be identity from the left and also from the right. Okay, but using this thing, we know that if G is already a group, and if we can see that one element is acting as a identity when it is being operated from the when we are operating using that element from the right, then automatically it will be a identity from the left also. But again, note that this is after we have the information that G is a